So we're gonna go through proof 7, which which is that the different bases have the same number of elements. That okay. So we've got to prove that two bases of an abstract vector space V have the same number of elements, using the fact that if a matrix is invertible, then it is square. Okay. So we will start by considering a basis V, which is made up of V1, we have to Vk with k elements, and um, another one which is W, which is W1 all the way up to, this one has k elements and WP, and this has 3 elements. Alright, um, so there are some concrete to abstract functions such that r of k goes from yc, sorry, IV, right? That's the transforming to this vector space V. And there's another one which goes from W from R of P. Right. So what we want to do, we want to argue that the following are true for these two functions, uh, which is that IV is 1 is to 1 because basis vectors are in fact linearly independent. So for all x, maybe write this down. 1, 2, 1 is because for all x element of V, if x equals phi a equals phi a b, then equals mark here equals 1 vi vi, and also sigma k I minus vi, and I is equal to 0 vector. So for all I ei is equal to bi. This is essentially kind of the proof that we did in 23A at some point of time. So I'm just sort of regurgitating that logic back here. Um, the second thing is that is also, so phi v is also onto because all basis vectors are spanning. So what I mean by that, so phi v is onto, um, and that is because for all, oops, for all x element of v, I will take k, I don't have enough space. values. So this is 1 A I V I. So this is essentially the same as writing x. That vector x is the transformation of phi v of the vector a. So since it's both invertible and onto, that would mean that the inverse of this also exists, and the functions therefore would be something like r of, are we going back to what we started with? So we can apply the same argument for the phi. Well, we already know that um, the other one is, no, we don't know, but we could use the same argument to figure out that the other one is also invertible. So this can be written down as phi v minus 1 inverse embeds into this vector space v, which then in fact we don't need the inverse of the other one because we start with the same thing. So rp. All right, so what this would mean that if I compose phi v minus 1 with phi omega, we would then get a concrete vector in rp all the way up to rk. Therefore, it must be a matrix which has size k by p. Also, the composition of two invertible matrices is invertible, so kp has to then be invertible, and kp since only square matrices can be invertible, that must mean that k equals p, and therefore there must be the same number of elements here and here.